Today I would like to discuss two nonlinear classification models with the help of a simple data set and some visualizations. Many machine learning problems in the real world cannot be solved by a linear equation. Let's consider the car evaluation data here. In the data, the concept is about the evaluation of a car, whether a car is acceptable, unacceptable, given its buying price and maintenance cost. The price and cost variables originally are on an ordinal scale, from low, medium, high to very high, which we have converted into an equal interval numeric scale from 1 to 4. 1 meaning very low cost, and 4 meaning very high cost or price. While it is possible to include other variables such as the number of doors and safety features in the data, here we will focus on the cost factors in the discussion. Because we limit ourselves to only two variables, it's easier for us to go through the math as well as the visualization of a two-dimensional space. And the plot here shows the maintenance cost versus the buying price, with the pluses, the blue pluses indicating acceptable cars, and red circles indicating unacceptable ones. The two classes appear to be separated, but it is difficult to draw a linear function or a straight line on the figure here to separate the two classes. So the two classes are separable but not linearly separable. We have discussed the support vector machines, or SVM, which in its original version is a linear model. So if the data are linearly separable, we can use SVM. But can we use SVM for nonlinear data? Perhaps instead of thinking about applying SVM to nonlinear data directly, we can think about finding a way to transform the data first into a different space in such a way that are linearly separable, where we can apply SVM. And so this is the idea of Kernel SVM. In particular, if we have this two-dimensional data with V1 and V2, we can perhaps find an additional dimension to which we can project or transform the original data to, where the two classes in the higher dimensional space can perhaps be separated linearly. Now, if we talk about a three-dimensional space, a linear function on a three-dimensional space is a surface or a plane. And so we can use a plane to separate the two classes in the higher dimensional space. And the projection or the expansion and transformation of the original features is through something called a kernel function. A kernel function is a very efficient way to compute new dimensional data based on the original dimensions. Among families of kernel functions, a polynomial function is often used. So for example, we may consider a quadratic transformation with the car evaluation data. Here, given two existing variables, any data instance with V1 and V2, a two-dimensional vector, can be expanded onto a vector with more dimensions, such as V1 squared, V2 squared, and V1 times V2. Note the quadratic expansion should result in 5 dimensions, including the original dimensions V1 and V2. For now, we'll focus on the 3 additional features, and so that we can limit the number of dimensions to 3, which we can visualize. With the V1 square and V2 square transformation, data in the two classes can already be separated potentially linearly. So as you can see here, on the two dimensions with V1 square and V2 square, we can potentially draw a line to separate the two classes. However, this does not necessarily represent the general idea of car evaluation. The boundary is very narrow, and new data may cross the decision boundary and violate the identify rule, the identify linear equation here. So the model perhaps is underfitting. So let's include the additional dimension of V1 times V2 in a quadratic transformation. This product of V1 and V2 can be actually seen as an interaction variable in the form of multiplication. That is, whether a car is acceptable or not may depend on some form of interaction between the buying price and the maintenance cost, V1 and V2. Take a look at the higher dimensional space when all these three features are considered. V1 square, V2 square, and V1 times V2. Of all the linear equations formed by 3 points in each class, we have identified two planes closest to the opposite classes. So as you can see, we have visualized the two planes here. Now in SVM, in support vector machines, the idea is that we can identify support vectors. Let's start with the two-dimensional one just to review a little bit. So on a two-dimensional space with two variables, V1 and V2, if we have data points in two classes, for example, and so on a two-dimensional space, we need two data points to form a linear equation. And the conditions for candidate support vectors are, first of all, for these two data points to be considered support vectors, the line that they form should divide the two classes. So first of all, the data points in the same class should fall on one side. And the data points from the other class should belong to the other side. So this is the idea of SVM on a two-dimensional space. The 2 points should form a linear function, a straight line that meet those two conditions. On the three-dimensional space, however, 2 points are not enough to form a linear function, because a linear function on a three-dimensional space is a plane, and it requires 3 data points to form a plane or surface there. So here we need 3 data points at a time to be considered as potential candidates for the support vectors. And so here, as you can see, these are candidate support vectors that form a surface, a plane. And if you take a look here, you can see that the red data points, the circles, are on one side of the plane, whereas the blue ones, the positive class, the data points in the acceptable cars are on the other side. Okay, so these 3 data points are potential support vectors. We can actually find the closest data point on the other side and draw a line perpendicular to the candidate plane linear function, and this will become the margin between the two classes. Because we really focus on the support vectors that are kind of the borderline data points closest to the other class, let's zoom in on this area here to take a close look on the support vectors. To help with the visualization, we'll also project each surface to the ground, to the V1 square and V2 square dimensions. So these three data points, the three data points here form a linear function. And we can find the closest data point from the other class, which is right here, and draw a line perpendicular to the surface here. And this defines the margin between the two classes. So if we indeed find out that this margin is the greatest among all potential candidates, then these three data points plus the nearest one, these four forms become the support vectors for the classification here. And the linear function can be identified at the middle of the margin. Again, the linear function here is not just a straight line, but it's going to be a surface, that separate the two classes. But you can see from this projection, this kernel function transformation, the original data that are not linearly separable become separable linearly on the three-dimensional space. So this is an example of the quadratic expansion, so that we can obtain a higher dimensional space where we can apply SVM for linear classification. Besides polynomial kernels, there are also other kernel functions for SVM, such as radial bases and string kernels. A string kernel, for example, operates directly on simple sequences without vectorized features and is useful in applications such as text classification and gene sequence analysis. Let's look at another nonlinear model. We know that a single perceptron can only be applied to linear data, but the car evaluation data here cannot be separated by one linear function. With the step function, however, we can transform the data into something linearly separable. Specifically, for value v, either on the v1 or v2 dimension, that is the buying price or maintenance cost dimension, we can use the following step function. If v is greater than 2.5, then the output of that function would be 1. If otherwise, the value of the output will become 0. So this is a very simple step function, and what it does is this. So it returns 1 for value above 2.5 and 0 for value below. Applying the step function to the v1 and v2 dimensions respectively is equivalent to have a cutoff line on the dimension. So we know the f function here is going to evaluate 1 for v greater than 2.5. And if it's something less than 2.5, it's going to be 0. So this is going to create, for example, for v1, this is going to use a threshold or a cutoff value at 2.5. And if a value is less than 2.5, it's going to be 0. If it's greater than 2.5, it's going to be 1. And the same on the v2 dimension for the maintenance cost here. If it's above 2.5, it's going to be 1. If it's less than 2.5, it's going to be 0. And so with this transformation, let's use H to denote the transformed dimension. Okay, so H1 is the transformed V1, and H2 is the transformed V2. So if we look at the transformed dimensions H1 and H2 here, the original data points, for example, the red data points will actually become the red circles here. And this cluster will actually move here. And the cluster here will be moved here, whereas the blue class, which were originally here, will all be transformed to 0 values. 0 on the V1, 0 on the H1, and 0 on the H2. Okay, so after this transformation, you can identify a linear function such as H1 plus H2 equal to 0.5, which is the straight line here to separate the two classes. So the transform data are now linearly separable. The nonlinear classification with step function transformation can be represented with a multi-layer neural network. So again, this is the visualization for the step function that we discussed, right? So the cutoff on each dimension is 2.5. Okay. Now this 2.5 value can be represented as the weight for the bias. Here we only have one hidden layer. Let's go through this neural network to see what it does. So we have a hidden layer here, which is really applying the transformation, the data transformation. And the transform data values are called H values, H1, H2. And the input is the V1, which is the buying price in the Carvier variation data, and V2, which is the maintenance cost. Let's look at V1 first. So here it says V1, and then the weight for V1 is 1. And then there is a bias variable with value always 1, and the weight is minus 2.5. So let's say the sum for hidden node 1 is S1. And so this S1, the sum, is the weighted sum of the input values, which is the weight of minus 2.5, which is the weight for the bias, times the bias, which is 1, plus the weight for the input value 1, which is 1, times V1. Okay, and H1, the output value, activation value for hidden node 1 is a function, is a step function of S1, which is going to return 1 if S1 is greater than 0, and return 0 if it's less than or equal to 0. Okay, so the cutoff is really at 0 here, but with the weight for the bias of minus 2.5, the cutoff is actually at the 2.5. So the separation between 0 and 1 at the hidden layer is really this linear function of minus 2.5 plus V1 equal to 0. Or I can say V1 minus 2.5 equal to 0, which creates the cutoff at 2.5. So this is the same of the visualization here, where you have the cutoff at 2.5 for V1. V2 is the same. Okay, so that this transformation also creates a cutoff at 2.5 here. Okay, so from V1 and V2 to H1 and H2, this is the transformation that we discussed earlier, just to transform the data points to the H1 space, to the H1 and H2 values in this way, where they can be linearly separated. Okay, and so given the transform H1 and H2 value plus another bias in the hidden layer, we can actually find a linear equation such as H1 plus H2 equal to 0.5. And so the weights from the hidden layer to the output, the weights here actually represents a linear equation that separate the transform class. So let's take a look again. So this is essentially the sum S at the output layer is H0 times W0. So this is essentially W0, which is 0.5. So we have 0.5 there, plus minus 1 times H1. So this is actually minus H1, plus minus 1 times H2. This is essentially minus H2. Okay. And again, we see that if it's above 0, it's going to be 1. If it's below 0, it's going to be 0. So the separation line is really when this is equal to 0. Okay. And so this is the linear equation that separates the two. If we rearrange the variables, this is exactly H1 plus H2 equal to 0.5. The same linear function that we discussed earlier to separate the transformed data on the H dimensions. So we see that the multi-layer perceptron can transform the data using the hidden layer, and then finally at the output layer we can use a linear equation to separate the data. But how can we identify the weights together with the step function to build the multi-layer perceptron for such nonlinear classification? It is tempting to use a similar strategy as we discussed in a single perceptron model, where we can update the weights using the values in the input data. But because the model of the multi-layer perceptron is nonlinear, so the idea of using this linear strategy for weight adjustment actually turned out to be not applicable. So we need a different strategy here, because simply adding or subtracting weights does not help when the model is nonlinear. So how can we adjust the weights in a nonlinear manner during the training? In other words, can we adjust the weights based on how much each variable contributes to the errors in the final output via the hidden layer? The general idea here is that we can use a technique called gradient descent that makes it possible to find the optimal values and weights by searching in the derivatives of related functions. So the idea here is that we can, when we train the model, we can compute the prediction error. And we can take the derivative of the error with regard to the weights from the hidden layer to the output layer, as well as from the input layer to the hidden layer, and adjust the weights according to the derivative. But the problem here is that with the step function, and as we can see, a step function like this, okay, which is the f function that we discussed earlier, right? When something is greater than 0, it becomes 1. When something is less than or equal to 0, it becomes 0. So the function can be visualized here the cutoff is at 0, and then when it's greater, it suddenly becomes 1. When it's less than, it suddenly becomes 0. Okay, so there is a sudden jump in the function, and it's not smooth. And we know that in order to compute the derivative of something, the function has to be smooth. And so instead of having this function that is not differentiable, we should instead using a function that is smooth, some kind of smooth function that is similar to the step function, which can help us transform the data, but is something differentiable so that we can take the derivatives to update the weights. A candidate is a sigmoid function, which for value v can be defined as a function here. So here is the functional form of the sigmoid function. When the value v is 0, the return is 0.5, the middle point. When v is much greater than 0, it gets very close to 1. When v is much less than 0, it becomes very close to 0. As you can see, the functional form of a sigmoid function is similar to a step function, but it is smooth so that you can compute the derivative of the function. Generally, the sigmoid function can also be written as this with the parameter k, where k is the pivot value. So just now, when we talk about the first sigmoid function without the k, essentially this is k equal to 0. So the middle value is at v equal to 0. Now, if we have a k here, such as k equal to 5, the middle value is when v equal to k, which is 5 in this case. Okay, and this is where the curve pivots. So you can see that the sigmoid function is moving this way below the pivot value, and then it turns. The function turns after the pivot. That's why this k is called the pivot. So we can use the sigmoid function in place of a step function. And so if we adjust the previous neural network earlier with the sigmoid function, the step function becomes a sigmoid function. Okay, so here instead of using a step function for the weighted sum, we use a sigmoid function so we use a sigmoid function at the hidden layer as well as in the output layer. With the sigmoid function on each layer, the sigmoid function is differentiable, and so the weights can be learned from a process of the gradient descent, where we can compute the derivatives of the functions with regard to the weights and update the weights accordingly. So how do we learn the weights? Let's follow the network step by step. First, we need to feed the input values into the network. The weighted sum of each hidden node I, Si, can be computed by the sum of Wij times Vj, where m is the number of variables here, and V0 is the bias variable, which is always 1, and then V1 is the first input variable, v2 the second input variable, and so forth. So given the sigmoid function, the output of each hidden node is the sigmoid of Si. So let's look at the example here from input to the hidden layer. So again, the hidden layer node H1 is a sigmoid function of the weighted sum from the inputs here. Now in this particular model, we have two inputs. One is the bias, which is always 1, and the other is V1. Okay, so the weighted sum here is minus 2.5 times 1, minus 2.5 times 1, plus 1 times V1, 1 times V1. Now in this particular model, we do not have an input from V2 to H1, so the weight for V2 is 0 here. Okay, so this is the value for H1. And we can do likewise for H2 based on the input values of bias and V2. Okay, we get it here. The final output, or the predicted value y hat, is the sigmoid of the weighted sum of values from the hidden layer H values. So the output, final prediction, is the sum, weighted sum from the hidden layer. And we know that each hidden layer node is in turn the weighted sum of the input layer, and that's why we get this formula here. Now again, let's look at the model here. So the final output, final prediction y hat can be computed as the weighted sum from the hidden layer. Okay, again, it's a sigmoid transformation. Okay, so here we first have the sigmoid function. Okay, so this is the sigmoid function of the weighted sum. So W0 times H0, W0 times H0, W1 times H1, W2 times H2. Now, how do we learn about the weights? Now that we have a prediction, we can compare the prediction, the predicted value y hat, to the actual y value, to the actual class of the data instance. So depending on what the actual y value is, the actual class, whether it's 0 or 1, we can compute the error. And here we can define the error E as a square error. The error is basically the square of the difference between the actual value and the predicted value divided by 2. For prediction based on the sigmoid function, it can be shown that the differential with respect to the weight from hidden to the output, and we're talking about weights here, W0, W1, W2, from the hidden values to the output layer. Okay, so because now that we have an error, we make a prediction and we know how much the difference is. We want to adjust the weights so that in the future this error may be minimized. Okay, so this Fs, which an S is the weighted sum from the hidden layer, this is exactly y hat. Okay, so this is the predicted value minus the actual class value. Okay, the derivative of the error with respect to a weight Wi, whether Wi is W0, W1, or W2, is can be computed by the difference between the predicted value and the actual class times the derivative of the sigmoid function times the sigmoid of Si. Okay, so let's look at what these are. So we know this is basically the difference between the actual class and the predicted class. Fsi is the sigmoid of the weighted sum from the input layer. So this is Fsi is actually Hi, the output from each hidden node. What about the derivative of Fs? Okay, so the F prime S, the first derivative here, can be actually computed by Fs times 1 minus Fs. And we already know what Fs based on our prediction. So Fs is our predicted value, which we can compute. So it turns out all these values are something that we can calculate. And so if we can calculate this derivative with respect to each weight, we can use this derivative to update the weight so that the weight will get changed over the iterations, and hopefully this will tend to minimize the error. And eventually we'll find out the weights that can optimize the neural network. So what we are doing in this step is first to calculate the error, and then we want to take the derivative of the error with respect to each weight here and kind of propagate the error back to the weight to change each individual weight. And this is the idea of backpropagation. Okay, from the output to the hidden layer to update the weights here. Okay, but this is only the step 1 in the backpropagation. From the hidden layer, we also need to propagate the weights back to the input layer weights so that those weights can also be updated as well. So let's take a look at the derivative of the error with regard to the weights in the input layer. Okay, so we are talking about weights here, W10, W11, from the input layer to the hidden node 1, and then W20, W22 from input to H2. Okay, and so it turns out the derivative based on the sigmoid function is again the difference between the predicted value, again this is y hat, and the actual class times the first derivative of Fs times the derivative of Fsi. Okay, so Fs is the function at the output layer, and Fsi is the function for the hidden layer, which can be Fs1 here, Fs2 for the hidden node 2. And it turns out that the derivative of Fs in general can be computed by Fs times 1 minus Fs. And likewise, F prime Si can be computed by Fsi times 1 minus Fsi. So we can compute all these values without problem. Let's look at a particular example to see how these weights are actually computed and adjusted. So suppose this is one data instance from our training data with the buying price 2 and maintenance cost 2, and the evaluation is 1, which means this is acceptable. This is an acceptable car. Okay, so let's feed the data into the neural network. Of course, at the beginning, we don't know about the weights, so we're going to start with some initial weights. So we can start with some zero values. So all the weights at this point are 0. And now given the data instances of 2, so the V1 is 2, V2 is 2, V1 for the buying price, and V2 for the maintenance cost. So we need to feed the values into the neural network. So 2 for V1, 2 for V2. And we can compute for the node 1 here. We can compute, first of all, the weighted sum of the values. Okay, so it's going to be 0 times 1, 0 times 2, which is what happened here. We compute the weighted sum from the input layer, and then we take the sigmoid. If you remember the sigmoid function, at 0 point, right? So this is value 1, this is 0. So for the value that is 0, this is going to return 0.5. Okay, so that's what we get here for the sigmoid transformation. That becomes the value from the hidden node 1. And we could do likewise for hidden node 2, H2. Okay, again, we take the weighted sum from the input, and then we use the sigmoid function to transform the data, and again it becomes 0.5. For the bias going to the output directly, we can also use the sigmoid function, and because the bias is also 1, this is basically taking the sigmoid of 1, which turns out to be 0.731. Okay, so we have the values from the input layer. Now we can feed the hidden values into the output. Okay, so again, for the output, the S, the sum, is the weighted sum of the hidden values. So H0 is 0.731 times W0, which is 0. So 0 times H0 plus 0 times H1 plus 0 times H2. And then we take the sigmoid. Again, this turns out to be 0.5. Okay, so this is our predictive value from the output. And we know in the data instance, the training instance that we have here, the buying price is 2, the maintenance cost is 2, and then the class is actually 1. Okay, so we know y equal to 1 here. Okay, and the fs or y hat is 0.5. And so we can compute this, the error times f prime. So we can compute the difference of the predicted value and the actual value times the derivative of fs, and which turns out to be fs times 1 minus fs. So we can compute the values here. So why do we want to compute this right here? Because this part is a common part that we need to use. So this is what we need to use to compute the derivatives in later calculations. So you will see when we have this value already computed, it becomes easier to compute other related derivatives. Okay, so with this computed, let's move to the next stage where we can actually backpropagate the error. So the derivative of the error and the output with regard to each weight. So the derivative of error with regard to W0, for example, can be computed by Fs minus y times F prime S, which is what we computed just now, is minus 0.125 times H0, which is the value from the hidden node 0, which is the bias, okay, 0.73. And we can get the derivative to be a negative value, 0.0914. Okay, so now given this derivative that we computed, we can feed this back to the W0 value and update its value. So to update, we need to subtract the derivative from its current value. And so the current value is 0. And if we subtract a negative value, it becomes a positive value. Okay, so W0 will become positive 0.0914. And we can do likewise for W1 and W2. And again, the derivative is a negative value. And so when we update it, it's going to actually become a positive 1. Okay, the same for W2 as well. So now we finish one step in the backpropagation from the output to the weights for the hidden layer. We need to go one step further to adjust the weights to backpropagate the weights back to the weights from input to hidden. Okay, so again, we have discussed the formula here. The derivative of the arrow, so arrow eventually calculated in the output, the derivative of the arrow with regard to each weight from the input layer can be computed by this, again, this common component, okay, Fs minus the actual class y times F prime S, okay, and we know this is minus 0.125 times F prime S1, okay, the F prime S1 is the derivative of the F function for the weighted sum here, okay, so this can be computed by Fs1 times 1 minus Fs1. We know Fs1 is essentially the H1 value, so it's 0.5 times 1 minus 0.5. So in the end, there is also the value of V0, which is the bias variable here, which is 1. So we can compute the derivative with regard to the weight here. So this weight is for the bias. Okay, we can do likewise for the weight W11 for V1 to hidden node 1. So we can do the same thing, okay, to compute the derivative. And so these weights are going to, so these derivatives will be used to update the W10, W11, W20, W22 weights here, okay. So we see that they are negative values. So when we update them, for example, when we update the W10 weights, we're going to subtract the derivative from its current value, okay. And so current value at the beginning is 0. We subtract a negative value. This is going to be a positive value. Okay, so you can do this. We can do the same thing for the weights here. So with the backpropagation, we can update all the weights for each training instance given the arrow. Okay, so this is the weights that we have obtained after the first training instance. So we have obtained the positive weights here. And we can continue to train the model with additional instances in car evaluation data. And this can be repeated even with the same data, until weights are stabilized and the errors are reduced to a certain level. The figures here show relative weights and error over time via iterations of repeated training with data. Because in linear equations, absolute values of the weights or coefficients are not important. So for example, if I have a linear equation such as a plus bx plus cy equal to 0, I can divide both sides by 100 and still the same formula, or I can multiply this by 1,000,000 and still the same formula. Okay, so it doesn't matter what the absolute values are, but it's more important to look at the relative weights. Okay, so that's why here, instead of looking at the absolute values of the weights, we actually divide the weights by W. For example, we divide W11 by W10. And this W10 is actually the weight for the bias. To the output layer, we also divide W1 by W0, which is the weight for the bias as well. So here, the figure is to look at the relative weight over the number of iterations. So X is the iteration, Y is the relative weight. And you can see that the input layer weight, for example, takes more than 10 iterations to converge. So in the first 10 iterations, it fluctuates quite a bit, and then it gradually converges, stabilizes. For the weights to the output layer, it looks like it takes longer to converge. Here you can see it takes more than perhaps 300 iterations for the weight to converge. It takes even more iterations for the arrow, the square arrow, to converge over time. Okay, so you can see at the end, the arrow is minimized at this level, but this is not so until at least 1500 iterations. The table here shows the weights of the converged model using backpropagation. We can look at the absolute values, but we can also look at some of the relative values based on different factors and normalization. So one set of values we want to look at is this, after we normalize the original absolute values by a certain factor. So the W0 is minus 1.9, okay, which is here. Okay, so we can put the values back into the model, and this is what the model shows. So let's visualize the model using the weights here. Okay, the weights here actually also creates a cutoff at 2.5 for V1 and V2 with this W0 weights. And so this is equivalent to transforming the original data points here into the space here where the positive and negative classes can be separated. And the W0, W1, W2 weights represent the weights for the linear function, the line here, to separate the transformed classes. So this transformation is similar to the model that we discussed earlier, but not exactly the same. Given the limited training data we have, there can be many nonlinear solutions to the same classification problem. In the end, we obtain the model here, which is slightly different from what we proposed earlier. Both models will make perfect classifications on the small data set that we have here. However, a model obtained this way has not necessarily found the global optimal. In fact, the backpropagation mechanism via gradient descent can converge to a local optimum, which depends on many factors, such as what the initial values are, the sequence of the training data, and so forth. The learning rate also has an influence on the convergence of weights, and occasionally may also influence where they converge. So in this lecture, we discussed two nonlinear models, the SVM, the support vector machines with the kernel function, and the multi-layer neural network. There's a similarity between these two models. In support vector machine, we use the kernel function to expand the feature space into a higher dimensional space where the classes can be separated linearly. In the multi-layer perceptron model, we also transform the data using the sigmoid function and then use a linear equation to separate the transformed data.